Hi guys, I'm Mr. Joseph, your chemistry teacher. I'm back with my lectures, still on rate of reaction. So the lesson objective for today's lecture, number one is describe the Maxwell-Boltzmann distribution curve of particle energy. Then the second one is sketch and use the Boltzmann distribution to explain the significance of activation energy. Then we're going to look at explaining qualitatively. We're going to explain qualitatively in terms of the Boltzmann distribution and of frequency of effective collision, the effect of temperature change and catalyst on the rate of a reaction. So please, I want us to listen attentively and get the best from today's lecture. Before us is Maxwell-Boltzmann distribution curve, Maxwell-Boltzmann distribution of molecular energy, which is a graph of number of molecules with a particular energy on the vertical axis and molecular energy on the horizontal axis. Now, this is the Maxwell-Boltzmann distribution curve. Now, experiments show that due to many collisions taking place between molecules, there's a spread of molecular energies and velocities. From our previous lecture, we are made to understand that for any chemical reaction to take place, there must be collision between the reactant particles. The excess of collision to generate energy is equal to the activation energy or more than the activation energy. So there's always a spread of molecular energies and velocities. Now, if you look at the graph, it starts from the origin. It starts from zero, which is the origin. So that's an indication that no particles have zero energy or velocities. All particles, no particles have zero energies or velocity. Some have very low energy and some have very high energies or velocities. Most have intermediate velocities. Now, if you look at the curve, within this region, this is the curve within this region. This is, the area with the most, this is the most probable energy. Most probable energy. So when we talk about the most probable energy, the energy possessed by the maximum number of reactant molecules at a particular temperature, at a fixed temperature, at a particular temperature, is the most probable energy. The maximum number of energy, the energy possessed by the maximum number of reactant molecules at a given temperature. Then you have, this is the mean energy. This is the mean The mean energy. The mean energy. So this gives a description of the Boltzmann distribution curve, that there is spread of molecular energies and velocities due to many collisions taking place between molecules. There are no particles have zero energy or velocity. Some have very low energy and some have very high energy, and most of them have intermediate energy or velocities. So the most probable energy, which is the energy possessed by the maximum number of reactant molecules at a given temperature, and above the mean energy. So it's as simple as ABC. So we're going to use the Boltzmann distribution curve to explain the effect of temperature on the rate of reaction and the effect of catalyst on the rate of chemical. So before us is Maxwell distribution curve, which is a graph of number of molecules with a particular energy against the molecular energy. On the vertical axis, you have number of molecules with particular energy. On the horizontal axis, you have the molecular energy. So the Maxwell distribution curve, is used to explain the concept of activation energy. When we talk about activation energy, is the minimum energy required for a reaction to take place. So if you look at the curve, you discover that the area under the curve beyond this is the activation energy, which is E. We use E to represent the word activation energy, which is the minimum amount of energy for any chemical reaction to take place, based on collision theory that we've treated in the past. That before any chemical reaction to take place, or before any chemical reaction can take place, the reactant particles must collide. The essence of collision is for the reactant particles to generate energy that is equal to the activation energy or more than the activation energy. When we talk about the activation energy, the energy barrier that must be overcome for any chemical reaction to take place. So the area under the curve beyond the activation energy, that is beyond this part, corresponds to the number of molecules with sufficient energy to overcome the energy barrier and react. So these are the molecules, number of molecules with sufficient energy to overcome the energy barrier. So these are the number of molecules that can react. So the Maxwell distribution curve helps to explain in detail the concept of activation energy. So which is the minimum energy required for a reaction to take place. So this is just the Maxwell distribution curve, and in fact we are going to look at how the effect of temperature on the rate of reaction using the Maxwell distribution curve, I'm also going to look at the effect of catalyst on the rate of chemical reaction based on what Maxwell Boltzmann distribution was called. So I want to look at the effect of temperature on the rate of chemical reaction. We'll be looking at increasing temperature. Now, from our previous lecture, we're meant to understand that for any chemical reaction to take place, there must be collision between the reactant particles. That the essence of collision is for the reactant particles to generate energy that is equal to the activation energy or more than the activation energy, so that I can overcome the energy barrier for reaction to take place. Now, what happens is that temperature is one of the factors that brings about increase in the frequency of collision of the reactant particles. So, we want to see the effect of temperature on the rate of reaction. It has been proven scientifically that for every 10 degrees in temperature, the rate of reaction doubles. Now, increasing the temperature increases the rate of a reaction. Particles get more energy, so can overcome the energy barrier, which is the activation energy. So particles speeds also increases, so collisions are more frequent. Now, if you look at what we have here, this is the Boltzmann distribution curve that is used to explain, the effect of temperature on the rate of reaction. Now, if you look at on the vertical axis, we have the number of molecules with a particular energy, then we have the molecular energy. So Maxwell distribution of molecular energy. Now, what happened? This is what we call the activation energy. This is the activation energy. From this point, this is the activation energy. This is the activation energy. So it is particles within this region that are able to generate energy that is equal to the activation energy or more than the activation energy where reaction can take place. So these are the number of molecules. Number of molecules with sufficient energy to overcome the energy barrier. So the activation energy is the minimum energy required for a reaction to take place. So the area under the curve beyond the activation energy corresponds to the number of molecules with sufficient energy to overcome the energy barrier so the reaction can take place. So for every 10 degree rise in temperature, the rate of reaction doubles. So as the temperature increases, the rate of reaction increases. As the temperature decreases, the rate of reaction decreases. That is why when we put our food inside the freezer, the temperature inside the freezer is very, very low. So for our food to go rancid, what happens is that it has to do with what's a chemical reaction. So it has to do with temperature. So the temperature inside the freezer is very, very low. So the rate of reaction will be very, very low. So that's why we can put our food inside the freezer, and meat, fish inside the freezer, and it will not get spoiled. It will not go rancid, because for it to go rancid is a chemical reaction, and the temperature is extremely low, so the rate of reaction will be extremely slow. So it's as simple as what A, B, C. That's it. So still on the effect of temperature on the rate of reaction, increasing the temperature. So we're going to use the graph before, which is the Boltzmann distribution curve we've considered in our previous lecture. We want to use the Boltzmann distribution curve to explain the effect of temperature on the rate of reaction. So if you look at the number of molecules with a particular energy and the molecular energies. So what happens is that we have the activation energy here. We want to look at the effect of temperature. Now when you increase the temperature, let's see, when you increase the temperature, what happens? The curve will go this way. If you look at the diagram we have here, the curve will go this way. So what you observe is that what extra molecules with sufficient energy to overcome the energy barrier. So the number of molecules that can react will now increase because there's an increase in temperature. So increasing the temperature gives more particles an energy greater than the activation energy. So more particles can react. More reactants are able to overcome the energy barrier and form products. So a small rise in temperature can lead to a large increase in the rate of reaction. Just as I told you in our previous lecture, that for every 10 degree rise in temperature, the rate of reaction doubles. So this is the graph representing what? Representing an increase in temperature. So this is the graph we go. So initially, these are the number of molecules that could react. Now we'll have more molecules that could react, because more molecules are able to overcome the energy barrier, which is the activation energy. So from what we have here, you can see that T2 is greater than T1. The T1 is the initial temperature. Then the T2 is when there's an increase in increase in temperature. So temperature is a major factor that affects reaction rates. Temperature is a major factor that affects the rate of a chemical reaction. As you increase the temperature, the frequency of collision of the reactant particles increases. More particles gain energy to overcome the energy barrier and can react. So it's as simple as what? A, B, C. So please, I want you to take note of the Boltzmann distribution curve and how it can be used to explain the effect of increase in temperature on the rate of what? On the rate of chemical reaction. So adding a catalyst, so we want to look at the effect of a catalyst on the rate of a chemical reaction. A catalyst is any substance that speeds up the rate of a chemical reaction and itself remains chemically unchanged at the end of the reaction. So what happened? The catalyst lower the activation energy by providing an alternative reaction pathway. So catalysts provide an alternative reaction pathway with a lower activation energy. So that means decreasing the activation energy means that more particles will have sufficient energy to overcome the energy barrier and react. The energy barrier is the minimum amount of energy required for any chemical reaction to take place. So at the end of the catalyst remains chemically unchanged at the end of the reaction. So a catalyst speeds up the rate of chemical reaction by lowering the activation energy, thereby providing an alternative reaction pathway with a lower activation energy. So we're going to see the effect of a catalyst on the rate of reaction using the Boltzmann distribution curve, and also we're going to illustrate using the energy profile diagram for an exothermic reaction. So it's as simple as ABC. So still on the effect of catalyst on the rate of a chemical reaction, adding a catalyst. So this is before us is a graph of the energy profile diagram for an exothermic reaction. You have the enthalpy in kilojoule per mole on the vertical axis and the reaction pathway on the horizontal axis. So we're looking at the effect of a catalyst on the activation energy in an exothermic reaction. From collision theory, we state that for any chemical reaction to take place, there must be collision between the reactant particles. That the excess of collisions for the reactant particle to generate energy is equal to the activation energy or more than the activation energy. So we'll say the activation energy is the minimum energy. Now, if you look at the reactant we have here, what happens is that the reactant particles has to collide to generate energy that is equal to the activation energy. This is the activation energy for the uncatalyzed reaction when the reaction has not been catalyzed. So the reaction has to collide to generate energy so that the product can be formed, so that the reaction can take place for the uncatalyzed reaction without a catalyst. But when you add a catalyst, what happens is that when you add a catalyst, what a catalyst will do is what? It will lower the activation energy by providing an alternative reaction pathway. So instead of the reactant particles to collide and pass through this pathway, a catalyst would lower the activation energy, providing another pathway with a lower activation energy. So this is the activation energy. So maybe the initial activation energy was about 350 kilojoule, but adding a catalyst can lower it to, let's say, 150 or 200 kilojoule. So more particles can react. So that is the effect of a catalyst. So this is the uncatalyzed reaction, and this is the catalyzed a catalyzed reaction. So a catalyst speeds up the rate of chemical reaction by lowering the activation energy, decreasing the activation energy, providing an alternative reaction pathway for the reaction to take place. So it's as simple as A, B, C. So I want to look at the effect of a catalyst on the rate of chemical reaction using the Boltzmann distribution of molecular energy. Boltzmann distribution curve. So if you look at the graph before us, you see that the activation energy, this here will have the activation energy. So we want to see the effect of activation energy. So this is where they'll have the activation energy. This is the activation energy for the uncatalyzed reaction when the reaction has not been catalyzed. So extra molecules of energy to overcome the energy barrier. So the effect of a catalyst from our previous lecture, we say the catalyst lower the activation energy by providing an alternative reaction pathway. So what happens is that by the time you add a catalyst, this is the activation energy. So a catalyst will lower the activation energy to this point. So let's say this is the original for the uncatalyzed reaction. This is the activation energy. So for the catalyzed, this will become the activation energy. So lowering the activation energy results in a greater area under the curve after the activation energy, showing that more molecules have energies above the activation energy. So you can see that extra molecules with sufficient energy to overcome the energy barrier react. So more particles, more molecules can react because the activation energy has been reduced. So lowering the activation energy results in a greater area under the curve after the activation energy. This is the original activation energy for the uncatalyzed reaction. But then you add the catalyst, this becomes the activation energy. So it's as simple as ABC. So you should be able to sketch a Boltzmann distribution curve explaining the effect of catalyst on the rate of chemical reaction, how catalysts affect the rate of chemical reaction by lowering the activation energy, resulting in the greater area under the curve after the normal activation energy for the uncatalyzed reaction. I'm Mr. Joe, your chemistry teacher. Subscribe to my YouTube channel, like, share, comment, and reach out to me if you encounter any difficulty while going through the videos. Please reach out to me. I'm always there for you. I'm Mr. Joseph, your chemistry teacher. Thank you for listening.